But before we can talk about scheduling, we need to understand synchronization. Now, synchronization is something which you already know to some degree. Who has heard concurrent systems here at the ANU? Most of you, not all of you. Okay. Who heard concurrent systems with me? Okay, almost all of you. Okay, cool. That means the next chapter will be fast forward. Synchronization mechanisms. Moderate me. I will be going fast forward, and you tell me when you start panicking or when you don't remember stuff. And also for the benefit of the handful who have not heard concurrent system and concurrency and synchronization here. You have had some synchronization concurrency lectures before someplace else, I hope. Yeah. Okay. Good. Goody. Can you tell us what a semaphore is?
It's like when you, I remember the lecture said something about, so the analogy is an oil rig, you use the semaphore when you check in.
Mm-hmm.
It's like a, so then you have like a check in, and then you have a semaphore, and then you set it to your working environment, and then you put it in another bin.
Yeah. If you wipe away for a moment all the fluffy train and traffic light and God knows what metaphors which are often used in that one, if you just nail it down to what is technically a semaphore, hardware architecture, CPU architecture, what is a semaphore? How does it look like on the machine? It's a number.
It's a variable with atomic test and set.
It's a variable with atomic test and set. Mm-hmm. Okay. Why do you bring atomic test and set into play now? Do you understand why this is now coming to play?
So, yeah, if the semaphore is active, somebody has access to that resource and nobody else can get access, and then it's available again.
Yeah, this is how it's used. I'm asking about what it is.
So the semaphore is a variable with two operations, P and D, where P is something along the lines of if there is currently no process suspended on this, then reduce its value by 1, else suspend yourself on this process. And V is if there is something suspended on it, release it, else increase the power.
Yep. Full marks. This is the technical definition of a semaphore. And in order to implement that, now you're coming into the game, in order to implement that, you need some underlying atomic operations. Like, for example, test and set, or atomic exchange, or memory reservation, or any other atomic scheme to actually implement that underneath the hood. So the classical second-year exam question, can you implement a semaphore in a classical C compiler without any further support of anything? No, you cannot. Say again? Bakery algorithm is crude. Because this was a very nice textbook example back in the days when you had no caches and single CPU lines. If you have multi-core environments and shared caches between multiple CPUs, your bakery algorithm is not going to cut it. Unless you splice into your bakery algorithm lots of flushing all the time. So you can save it. But the bakery algorithm was big enough in the textbook version, as you remember, right? In order to make this really work on current hardware, you would need to expand that further to make that go. And still, you do rely on some atomicity assumptions also in the bakery algorithm, right? There's not a question whether you do have to make atomicity assumptions, yes or no. The question is, what is the level of comfort of your atomicity assumptions. The Bakery algorithm assumes that you have atomic access to a single memory cell, which is also an assumption. So you cannot half-write a memory cell. Right? And you can do that. But of course, in real life, you have a little bit more CPU support than that. So what else did we discuss? Monitors, mutexes, protected objects, obviously, atomic blocks of all sorts, conditional critical regions. Is this atomic? You probably see this plenty in concurrent programs. Somebody reads a memory cell in one thread, increments it in another thread. Looks beautifully atomic, right?
No.
It doesn't look beautifully atomic.
Well, it's not.
It's not. Could it be atomic?
Yeah, it depends on the language. She had these crude instructions.
Yeah. Maybe you work on a instruction set which actually has that.
That almost looks like some kind of compare set. Like the one on the right could very well be implemented with one instruction.
Yeah. Yeah.
Atomic compare set.
Yeah. Okay. Okay. Okay.
And it's not a fast for it to have an atomic increment.
Yeah. Maybe my I is stored in the register, shared between these two threads. Maybe I do have an atomic increment on a register. What? So yes, I could fantasize. And maybe true. How many assumptions do I have to make? I have to make assumptions about the memory bus size of this machine. I have to make assumptions about the memory alignments. I have to make assumptions about the instruction set, possibly even the scheduler. So even for these very, very simple assumptions, very, very simple cases, it is unrealistic to assume any kind of atomicity there. Okay, that's not any kind of an issue for you. You see that kind of code and you tell the programmer off, right? That's rubbish. Good. So we need a bit more than that. Synchronization by flags. Can we do that? We assume that we have atomic access to symbol memory access. Can I do something like that? Would that be working? It's not a semaphore, it's a flag. Just a shared variable. That's it. Would that be working? You think so? Maybe?
Assuming they share memory.
Yeah, sure. They're nice, they share memory. Sure, that works. But does it expand to, say, 3 tasks? Does it expand to situations where you want to set this flag back to false? So a single transition from one state to another state, globally observable. This can be used as a trigger. Emphasis on a single transition here. If I want to flip this back and forth a number of times or involve a number of different processes in the process, this is rubbish. Still, you will see a lot of code in real life which uses things like that. And I see this plenty in student code and exams that people are trying to apply and defend these kind of mechanisms with all their heart blood. This is just obviously so simple and obvious, it has to work. So they're trying really hard to do just that.
Yeah, just on that, if you're saying you can swap from one to the other with one go, can you not put the whole thing in reverse in a loop? The swap back and forth as many times as you need?
If I...
One instance of that, then the reversal flips back, so to speak, then the whole thing will loop.
Yeah, of course you can expand now slowly into a number of more cases which could just be working. The problem is the brain power which you need to actually guarantee that this is the case is much more than using a synchronization mechanism which is guaranteed to work in the first place. So you wouldn't do this in practice, ever. And in almost all cases where students present this to us in exam papers, for example, in almost all of those cases it is actually wrong. It's so easy to actually slip out of that one. You're right to say that you can expand that beyond this case here. So there could be a few more special cases, but it doesn't really help you in practice. So that's rubbish. And that was your 100% answer for the, what is a semaphore? Right? Okay. And if you're a semaphore, then this is actually going to work, but it's also clunky as hell. Mutual exclusion based on semaphores. Easy peasy. Do you have semaphores in Ada? Have you used them? Okay. So yes, you do in fact have semaphores in Ada. Barely any Ada programmer ever used them. And funnily, most Ada programmers actually have never heard of them. And this is called Ada synchronous task control, suspension objects. I think quite purposefully they didn't call it a semaphore, not to lure anything back into them. And they have quite specific instructions. They are not operating system level semaphores. They are more the Dijkstra original definition semaphores. They're queueless. They have no further waiting queues associated with them in any way. You're actually not able to suspend more than one task on them, otherwise you get a program error if you do that. Why do they offer that? Obviously it's really primitive. Because it's useful for what? No, if you need the semantic of a semaphore, you go through the full semantic of a semaphore. You go through a protected object. Why do you have to have that though? Yeah. What was your answer?
Maybe you want to go about synchronization constructs.
No, you can also do every other synchronization construct based on protected objects. That's not restricting you. Not directly. And not using that package for that. Now this has a different purpose here. This is for the CPU cycle counters. This is if you need to guarantee synchronization between two tasks based on 3 CPU cycles. Because this is nailed down directly to hardware synchronization constructs. It's simply going down to a test and set directly on the machine level. And there's no queue, there's no overhead, nothing on top of the whole thing. There's no task processing on top of that. This is the fastest task switch you can possibly physically do on a machine. And that's the reason why this is there. Only for the very special cases that you need to have a super fast task switch for a very, very simple synchronization point. it's not useful for anything else. It's just straight medieval if you try to, in any case, use that for synchronization in general sense. Of course, straight away you can construct a deadlock, but you can construct a deadlock with every kind of synchronization mechanism. That's not a big surprise. And you cannot suspend more than one task on the same suspension object here, because there are no queues. There's no overhead. There's no waiting queue. All the luxury which are used in Ada from protected objects that you have highly efficient implemented waiting queues and predicates associated with all thing, all of that thing is not here. That's quite a point on those kind of implementations. So, on the other hand, of course, POSIX semaphores are universally used. And have you used POSIX semaphores in your past life at some point? As you can see, lots of pointers being handed over. It's not void pointers, it's not that bad, but it's just a bunch of pointers, as always, and a bunch of integers. And the semantic of those integers changes depending on the context. You can read the value of the semaphore, and if the value of the semaphore is 0, you're not getting 0, but you're getting the number of processes which are currently suspended on the semaphore as a negative number. Type system. Welcome to integer and overloading of semantics. Just classical example of semaphore usage in POSIX. Why did I make you stare in second year on this example here? Do you still remember whether you figured out whether this works or not? It didn't? You didn't figure it out, or it didn't work? You didn't figure it out? Oh, okay. So you made the clever, educated approach of, who cares? Huh? And this is actually the right response. This is a nice exercise, so if you're into logic puzzles and things like that, you can now spend the time to find out whether all the paths are possibly leading to the right outcome, whether you don't have too many weights and too many signals balancing each other out in the wrong one. But the actual point of this exercise here, of this thing here, is that this is tremendously complex, even on very simple examples. And yes, it will take you probably 2 to 4 minutes to figure out whether this works or not. And the scary part is, if I ask you after 5 minutes, are you sure? You will still go, mostly. Huh? And that's the point of this kind of exercise here. Okay. So using POSIX and using semaphores in the real world for somewhat anything beyond an absolutely trivial example is very unusual, and you should definitely avoid that. Semaphores in Java is funny. When I look at this one, I always have the impression that they didn't explain to the Java guys what the semaphore is, because that's the Java semaphore interface, and in the classical Java way, make it comfortable. I have tons of possibilities how to interact with that one. It's just an access to a variable with tons of additional possibilities. You can read it, you can take a number of them out, number of them in, checking and manipulating it in all kinds of ways. That's not the point of a semaphore. The point of a semaphore is that you only use them for synchronization mechanism, not to share data in some way. So that's pretty confusing to do that. Okay. But you do have wait and signal, which is called acquire and release in Java. Interestingly enough, even that very primitive synchronization mechanism has only been invented in 2004 in Java, quite a bit going into the Java development already. Okay, semaphores. I hope you are beyond that point and using a little bit more grown-up synchronization mechanisms in your actual systems, unless you just simply don't have a choice. And maybe you have enough time, if you don't have a choice, to construct something more powerful on top of semaphores before you actually use synchronization mechanisms. So you still have the possibilities to just abstract it yourself before you just directly use semaphores here. Conditional critical regions, what was the idea there? You had the condition which you want to test before you go into a critical region. You have this condition actually explicitly coded and associated with the critical region. So far, in those semaphores, what you're actually waiting for is in your head. It's not syntactically connected with the semaphore in any way. The semaphore is just your wait operation, your signal operation. That's it. What you're waiting for is in your head, because you're signaling from God knows where. Under which condition you're signaling can be anything. This is actually associating a predicate with the whole thing. What's missing? It's still a fully distributed operation, because these critical regions and the predicates associated with the critical regions can still be appearing anywhere in your code, which means the problem of scattering across a large project of your synchronization mechanisms still applies. How to solve that? What's the next logical step in terms of synchronization? Exactly. Call a monitor. You pack all the critical stuff into one section, which makes you now happy from the perspective of verification, from the perspective of checking something locally to be correct once and for all, and then you forget it. So you have, for the first time in any of these synchronization mechanisms, you have the power of modularization. That you define a module which has a certain set of synchronization characteristics to them, you verify this as correct, and you're done. Everything before that was impossible. You added a single signal operation anywhere in your project, and the whole semantic falls over. The whole semantic changes into something completely different. Here, you cannot do that. You only have access to that from inside these monitor constructs. And there used to be languages which actually have an explicit monitor construct, and they're still coming again. It's not exactly a very recent concept. Monitors have already been around since the mid-70s. And how do you do the signaling of the whole thing? How do you wait for a certain condition? Thank you. But we don't need this. It's all in your head, right? How do you wait for a certain condition in a monitor environment? Monitors give you mutual exclusion for free. Mutual exclusion is simple, easy to verify. But how do you get back to the monitor in case you want to wait for a specific condition to turn true? How do you make them sleep first?
Do you only do it when someone modifies the data in the monitor?
Yeah. So assuming classical, you want to program simply a queue, a buffer of some sort by means of a monitor, which means you want to only be able to enqueue something if the queue is not full. Very simple example.
So when someone calls .enqueue, they can read out any else.
Now, how do you associate this condition with it? If somebody calls enqueue and the monitor is currently open and free, who is stopping this process from just going into enqueue? Nothing. How do you suspend this task? Because you don't want to have this task enqueuing something because your queue is full. How do you make this task sleep?
You still need some sort of underlying, say, like a semaphore or something?
I need a semaphore. Yeah. It's basically exactly what it is. So you have a semaphore, but a restricted form of a semaphore. Do you remember what this is called? This restricted form of a semaphore? This is called a condition variable, which is technically a semaphore, but it is scope-wise associated with a specific monitor, so that you cannot use this semaphore, you cannot suspend yourself on the semaphore from anywhere outside of it. You have to go into the monitor to suspend yourself on that. So you have still a little bit more locality, but inside of the monitor, you still have condition variables which are nothing else than a hidden semaphore inside of the whole thing. Then you have the problem of multiple tasks inside the monitor at the same time. Because you enter the monitor, suspended yourself on a condition variable, somebody else can enter now. So logically, you have not all of them running inside the monitor, but they're operating inside the monitor. Some of them are suspended, only one of them is running. But logically, you have still multiple tasks inside the monitor, which is, for verification purposes, a nightmare. Because you would like to get this done with, go through the whole operation, exit the monitor. That would be a clean way of verifying your code. If you have to verify all the possible interruption paths, that's much more complicated. And there are different suggestions, or used to be different suggestions in the 70s and 80s, how to get around that one. Kicking tasks out the moment you, for example, send something. Forcing tasks to regain or reapply for access from the outside once they are reawakened. All a bit clunky. How does it look again in different programming languages? POSIX comes to mind. There's also something which is called monitor, which is called a mutex in POSIX. Now it's becoming pretty complicated. You have a large set of attributes there. What is a big problem, of course, if you use a mutex, is that a monitor, the point of a monitor is a scope. Right? You declare a region in your code. This is my monitor section, my scope of the monitor. This is a bunch of library calls. These bunch of library calls have no concept and no idea about scoping. Right? Which means you can call them out of order. The semantic of POSIX monitors in this spot is pretty funny. You have a signal and a broadcast on the condition variables of the POSIX semaphores. And the semantic of this one is if you signal on any of these condition variables, at least one thread is being released. At least one. Say again? Well, if you only suspend one of them, then exactly one is being released on that. If there is nobody waiting on that, then nobody is being released on that, of course. But if you have more than one thread suspended on that one, then you get at least one released on that one. How do you handle that? If you want to implement for example, any form of mutual exclusion. If you want to implement that, you want to enable now a task to add one more element to your queue. Because you found out there's one free space, I want to signal to a task, please, one task can now put one more element in my queue. This semantic is shooting yourself in the foot. Are these guys just lazy? Why have they done that? Why didn't they give you a semantic of, if I signal, I release one task, one process, one thread? What you have to do now, if you use this POSIX interface for mutexes, you call signal, and all the tasks which have been waiting have to reevaluate. All of the tasks have to check, was it me? Can I do that? And one will progress. Everybody else has to put himself to sleep again. So logically, you don't program any different if you call signal or broadcast, because in both of these cases you know that you could activate more threads than you actually wanted to. So all the threads have to recheck their condition, have to put themselves to sleep again, which is tremendously slow and non-performant and logically clunky. Again, why have the POSIX guys done that? If I would guarantee you that exactly one thread is being activated, that would have been much easier. Yeah, that's not the reason here. I can also do this on library level with that semantic. Anybody with enough hardware experience to do that, to answer that? There's a CPU architecture background to this answer, and that is that in a current symmetrical multiprocessing multi-core environment, it is simply hard to guarantee that without synchronizing across all of your cores. And before they do that, because they were too lazy to implement that in full, they rather threw it at the programmer, and you can handle then the fallout of that by having to put everybody else to sleep again. So you have to do this on the next level up. This is the most basic level, which works easily, can easily be implemented on all hardware architectures. And on most machines, this will actually only release one thread at any given time. The point is, it doesn't guarantee that. Okay. Calling that stuff out of order. Nobody knows what happens. This stuff can be called any time. Does it look a bit better now? Is that going to work? Looks a little bit more friendly. No? Doesn't look friendly yet. You have to follow a certain pattern in the whole thing. That's for starters. You have to make sure that you have to call the wait operation from inside a lock mutex, and you just have to check that manually. Just have to read the sequence in there. There's no scoping which will support you. You have to analyze the data flow of your programs manually. Not much what you can do about that one. So where do we have monitors? C#. And C# also associates data areas with these monitors, data objects which are to be protected by that one. Not fully scoped yet, but a little bit in that direction. And what works in C#, of course, works in Visual C++. And for the BASIC fans among you, of course, this also works in Visual Basic. To do this in Java, There is a monitor construct there, but again, this is just convention. This is not associated with the actual Java objects. Classical way, only using the language primitives in Java. I'm not going to torture you with that. There's a lot of Java code to go through to do this cleanly in Java. Just don't do that in Java. Okay. Other aspects of object orientation and these kind of synchronization points. Inheritance anomaly. If you have a language which is based on inheritance all around, you have to keep in mind that if you have synchronization points in your game, then you have to be extremely careful with inheritance. Why? Because these guys pointed out there is an anomaly. What does this mean? What kind of anomaly is that? What's the normal expectation you have if you inherit something? What assumption do you make if you inherit from a class and create something new? What do you assume to be holding true in this case?
All the properties and guarantees that superclass makes
are not violated. So all the things which you verified on the superclass, assuming you did any verification on that, but all properties which you guaranteed on the superclass will not be touched by you inheriting from it. Right? That's the core foundation of any kind of object-oriented environment, because if that would be violated, you would need to re-verify your system every time you inherit something, which is rubbish. You cannot re-verify the whole zoo of your Java libraries every time you inherit something. That would be complete nonsense. And of course, you have this guarantee in object-oriented programming that you inherit something, you're not changing the semantic of the parent class. Not so if you have synchronization points at play. Your parent class is using monitors, semaphores, any synchronization point in its parent class. You inherit from that, you mess it up. You potentially mess it up. And you're not only messing it up for yourself, you're messing it up for the parent class. Why is that the case? A number of ways of thinking about that. If you verify and guarantee, for example, that all your synchronization points, think very hardware at the moment, all your weight and signal operations are in the right order, and they're all nicely balanced, it all works out, verified that, all cool. You inherit from that, what you do is you add more synchronization points in there. By adding more synchronization points, which affect the same locks as your parent class, you mess up the locking mechanism of your parent class. That's called the inheritance anomaly, and you have to be careful with that. Okay?
Make those locks private to the parent class, so you can't do that.
Yes, you can make it all private to the parent class, which significantly lowers its possibilities, because then you cannot synchronize over multiple methods easily. How do you get around that? Because assuming you still want to do object-oriented programming, how can you fix that? You notice how it's called a protected object in Ada? It's one of the most misleading names. Why? If you do object-oriented programming in Ada, you can, of course, inherit from your stuff. Fine. A protected object can be inherited from what? from an abstract interface. So you define an abstract synchronized interface, and you can inherit from this abstract synchronized interface with a concrete implementation called a protected object. That works. But why is that okay? Because the thing from which you inherited is abstract. Don't mess anything up concrete there. And the moment you derive from that, your protected object is final. You cannot derive from a protected object any further. Which means this is a one-step inheritance thing. You can only inherit from an abstract entity, and then it's final. Same for tasks. Tasks can also inherit from synchronized interfaces, but you cannot inherit from a task. Yeah? Task is also a final synchronization object. Okay, you can call this cheap, easy, but this is pretty much the state of the art. This is pretty much what you can actually do. Going any further with that, you cannot derive anything without re-verifying your whole system again, which you obviously don't want to do. Okay. Oops. The raging of Per Brinch-Hansen about Java. It's just pretty funny when you look at some programming languages which have just completely ignored anything which happened in the past, and unfortunately this applies to Java. Slowly we are getting around to repair the concurrency issues in Python, getting around the global interpreter lock, hopefully eventually. Also classical core mistakes which have been done early in the language. Nobody had the experience to foresee this in time. And then you're fighting with that for decades to come before you repair something like that. Okay. Nested monitor calls, nasty. What does that mean, nested monitor calls? You can call from within a monitor into another monitor. Is that okay? Good, bad, forbidden, dangerous, productive, useful? Would you allow it? That's another case of that. Not only calling another monitor call, but calling yourself. Can you call yourself? That's a problem. Why is that a problem? Not necessarily. If you call yourself, if you call the same monitor from within the monitor, what would a clever implementation do? Yeah. A clever implementation of that would realize that this is a call from within the monitor into a procedure of the same monitor. That's fine. I don't have to release the lock because I'm already in there. I own that thing. If I own this monitor and call another method on the same monitor, fine. No harm done. I just keep the lock and call that one. So a clever environment can actually resolve that.
If you're already in the monitor, why would you want to use the external entry points?
That's the point. If the language is clever enough, it will actually retranslate this. This is not an external call. It will actually retranslate this as an internal call and treats it just as if you would call a local procedure inside the monitor and actually not going through the whole locking mechanism from the outside again. Just short circuits that. This could actually be an advantage, yeah?
But the problem is if it calls something kind of conditional, entry to evaluate the conditional variable.
Yeah, we're talking monitors here, so we don't have conditional entries.
But you still have conditional
Yeah, that's independent of that at the moment. So the conditional variables are messy already anyway. We have to solve the conditional variables at a different level. This is only about nested monitor calls. You had another comment on that?
I was going to ask again if they would make that check. If they're doing one check application.
Yes, your Ada implementation makes a check and allows that. So your Ada compiler will actually resolve that for you. If you call a procedure inside a protected object, has to be a procedure, cannot be an entry. But that's the monitor equivalent. Huh? In a monitor, you have a bunch of procedures, and if you call in the same protected object another procedure, it resolves this as, well, this guy is already in the protected object, fine, just let it go. But we're talking about nested monitor calls into another monitor. Would you allow that? Is that fine? Not fine? Why not?
You can just call the monitor there, and from that monitor you call me back. Just wait on itself.
That would be a deadlock situation, of course, if you try to do that, because then you're trying externally to call back on that one, which means this is locked down. And the general situation is that you try to avoid performance loss by overuse of locking mechanisms. If I call another monitor from within a monitor, which means that my original monitor is probably still locked down. It means I leave a chain behind me of locked down monitors, which invites deadlock situations very quickly. And by the minimum, it actually reduces performance overall quite significantly, because then I have one process which has a whole chain of monitors all locked down, and nobody else can move anymore. So that's not great. How do you resolve that?
Oh, okay, so, well, just with different monitors, if it was strictly hierarchical,
Yeah.
it would be very nice, safe, good.
If it's only would be in one direction, yeah. If you have a global enumeration of monitors and you know that you're only calling lower numbers or only calling higher numbers of monitors there, still you have a chain of locked entities leaving behind you. So it would be a possibility to have multiple resources locked down, but you need to be careful to avoid deadlock, and you can do this by, for example, enumerating all of your monitors in some way. Fair enough. Okay. How do you resolve that if you don't want to leave a chain of locked entities behind you? You need to find a mechanism to drop the lock where you're leaving. Right?
What if you want that behavior?
No, you're welcome.
You are.
Yeah, you're welcome.
I put banned.
It's not banned. No?
Why does one go one banned then?
You get a serious compiler warning if you do that, and it tells you that this is strongly discouraged to do that. It's talking Ada at the moment. No? So in Ada you will get a compiler warning for that, and the compiler warning will tell you something along the lines of, you should not call potentially blocking operations from within a protected object. Because if you call potentially blocking operations from within a protected object, that means you invite the possibility of deadlocks, you invite the possibility of significant efficiency loss, and the general assumption of, if you do lock stuff down, you're only locking it down for the minimum necessary time. And you don't need to actually call another entry ever. In Ada, you can always rework this into a different sequence. You can always rework this into a sequence where you actually use a requeue operation, or you leave the monitor and leave the protected object and apply again from the outside, instead of leaving the whole thing locked down. Yeah.
So if the monitor chain, if we have a nested monitor, it's a chain of lockdown resources, why are we wanting to release these resources? Is it so that someone else can use them? Why
Yeah.
So I thought monitor calls are reasonably quick operations. So even if it did have a few layers, it would quickly do it and come back, such that the effort it would take to temporarily suspend or temporarily take these locks away, let someone else in do something,
Yes.
then leave, then come back.
Yes.
It doesn't really
Yes.
help much.
Yes. But your assumption, which you're making here, is that the monitor calls are reasonably fast. You can only make this assumption if you know that your monitor calls are not potentially blocking. The moment you allow a potentially blocking operation from inside your monitor call, this assumption is toast.
You can put a delay statement, give it a maximum.
It's also not allowed. It's also, you mean a select then? Sure. Yeah? Of dropping the call? Requeue statements. The requeue statement, what are those? Anybody remembers what requeue statements are?
Any task that is calling your protected object in this case will be, so it will not perceive it, but it will be moved onto a new protected object queue while that protected object swings. Bit of that.
Okay, let me try again. A requeue statement will take the current task and queues it up into either one of its own queues or another queue, and releasing the current lock on this operation. Actually, it transfers the call completely to another entity. It's not like a function call or a procedure call which returns back to that point. You're aborting your operations at this point and you're requeuing this to another entity. And you can actually remodel all of your chains of different operations, all of your different phases, what you want to do, into a chain of requeue statements instead of a chain of monitor calls. A chain of requeue statements will always release the locks behind you. And you're just waiting for the one condition which you want to be delayed on for the next step which you need to take. And all the resources before you are becoming available again. That's the point of using a requeue statement. And requeue statements, of course, are fine. They're not locking anything down. You don't get a warning for those. That's the escape route for this problem of having chains of lockdown resources. This, by the way, will also give you, later on when we talk about scheduling analysis, an automatic guarantee of deadlock freeness of your system. And you cannot override this warning. If you actually ignore that and block it in chain, your deadlock guarantees are down.
If you have two procedures in the one task and you requeue into the other procedure, is that seen as an internal call or an external? Like does it go requeue then goes into a protected object then into a procedure, or does it just requeue straight into the procedure?
Oh, and then we have to discuss how many queues are on protected objects to answer that question exactly. So it's not external in a sense of reacquiring the lock for the whole protected object, but it is directly requeuing on another entry. It is not going through the outside queue. I'm not sure I'm answering your question.
I think so. Yeah. So it doesn't go into the protected object queue, but it goes into the procedure queue.
Yes. Which means the task stays an internal task. It does not leave the protected object and comes from the outside again. You need that for also in terms of predictability, that you can guarantee that tasks which are already in there will be progressed as fast as possible without being able to be overtaken from somebody coming from the outside. Making maximum internal progress first is guaranteed by that kind of behavior. We'll come to that later. Okay. Blast from the past, this whole synchronization thing. You still feel comfortable with the terminology which we're using here and the synchronization mechanisms, you should actually be feeling reasonably okay with that. Slow us down if you need this in more slow motion. I still need to discuss a few more intricate details about the synchronization mechanisms in terms of requeuing and actual protected object synchronization. But there's only a few things more to cover, and then we have to talk about message passing, because this is also important that you still remember all the synchronization issues around message passing interfaces. Cool. And then we can go into scheduling. Hope you have great plans for a sunny long weekend. Enjoy.